Hello again, grade 7s. In today's lesson, I'm going to talk about what effect pressure has on temperature. And then later, once I assign work for the day, you're going to read in your textbook about different types of thermometers and then identify different scenarios where those different thermometers are best utilized. Learning outcome is to identify and explain uses of devices and systems to generate, transfer, control, or remove thermal energy. That's going to apply to the different thermometers you're going to read about in the book. That being the recording thermometer, the infrared thermometer, thermocouple, regular lab thermometer, and I feel like I'm missing one more of them, but you can read about it later on. Here's what we know. At sea level, there's a certain atmospheric pressure. At that atmospheric pressure, ice melts at 0 degrees Celsius and water boils at 100 degrees Celsius. If you go to a different atmospheric pressure, so if you have an elevation change, then the changes to pressure can affect the melting and boiling points of water. So ice might not melt at 0 degrees Celsius, water may not boil at 100 degrees Celsius if we can change pressure. A couple of examples of this. One, let's say you're skating on a sheet of ice. So this blue block is a sheet of ice and have these little tiny white squiggly lines. These white squiggly lines would just represent the trail that follows behind after you skate across the ice. A sheet of ice has a temperature that's something less than 0 degrees Celsius. It could not be 0 degrees Celsius because if ice was exactly at 0 degrees Celsius, then it would melt really easily and the ice would just be a giant swamp. I'm not sure what the exact temperature of ice is in a skating rink, but let's say it's negative 10 degrees Celsius. At negative 10 degrees Celsius, ice should not melt. It should not turn from a solid into a liquid. However, when you skate on the ice, you apply pressure to the ice. So there's this change in pressure we're talking about. And it turns out that this increased pressure on the ice can actually get it to melt at a temperature that's less than 0 degrees. So normally at negative 10 degrees Celsius, ice would not melt, but by increasing the pressure I apply to the ice, I can actually get it to melt at a lower temperature. When you skate and you look behind you, you see these little tiny trails that follow behind. And it's almost like these little tiny trails have like this very thin layer of liquid water on it. Well, that's because that increased pressure is turning the ice into water. I suppose another reason that would explain why the ice is turning into water is just due to the friction between the blade of the ice skate and the ice rink. And that friction would result in there being some thermal energy that would also cause the ice to melt. However, pressure does have an effect too. Example 2, altitude changes. As you start to go to greater altitudes, the air pressure gets lower. So, for example, the air pressure in Calgary in comparison to Vancouver, because Calgary is at a higher altitude, the air pressure in Calgary would be lower. As the air pressure gets lower, it makes it easier for water to turn into a gas. If it's easier for water to turn into a gas, that means the boiling point of water is lower at greater altitudes. So at sea level, the boiling point of water is 100 degrees Celsius. If you went to a really, really high altitude, like for example, the altitude of Mount Everest, I think the boiling point of water is somewhere around 70 degrees Celsius. So it's quite a bit lower. As a general rule that we will use, the boiling temperature of water is going to drop by 3 degrees Celsius for every 1,000 meters that you go up in height. So for every 1,000 meter increase in height, the boiling temperature of water is going to decrease by 3 degrees Celsius. Let's look at an example for this. Using this general rule, I want to calculate the temperature water boils at when located 3,500 meters above sea level. And then B, if water boils at a temperature of 88 degrees Celsius, determine what altitude we're looking at. I like to do problems like this by constructing a diagram that shows how the altitude and temperature is changing. So what I'll do is I'll draw a horizontal line. And I'm going to say this is 0 degrees Celsius. And this horizontal line represents sea level. Sea level has an altitude of 0. Now let's say we go up by 1,000 meters. If I go up by 1,000 meters, then my boiling point of water drops by 3 degrees Celsius. Whoops, let's change this here. There's to actually be 100 degrees Celsius. At a 0 meter altitude, our boiling point of water is 100 degrees Celsius. So if we go up by 1,000 meters, it would drop by 3 degrees Celsius, making this 97 degrees Celsius. Let's go up by another 1,000 meters. So now we're at 2,000 meters. Go up by another 1,000 meters, our temperature would decrease by another 3 degrees. 97 minus 3 would be 94 degrees Celsius. Let's go up by another 1,000 meters. So now we're at 3,000 meters. And our boiling temperature would again drop by 3 degrees Celsius. 94 minus 3 would be 91 degrees Celsius. And let's go up again. And then at 4,000 meters, our boiling temperature would drop again by 3 degrees Celsius. Now we're at 88 degrees Celsius. Okay, let's answer these questions. So it says, calculate the temperature water boils at when located 3,500 meters above sea level. Okay, this is kind of like an in-between altitude. So 3,500 meters would be between 3,000 and between 4,000 meters. So 3,500 is going to be the exact midpoint altitude between these two numbers. So we could draw that with a horizontal line. Okay, so if 3,500 is the midpoint altitude between 4,000 and 3,000 meters, then the boiling temperature we're looking at would also be the midpoint between 91 and 88 degrees Celsius. If you want to calculate a midpoint between two numbers, we can just take the two numbers and add them up. So you'd have 88 degrees Celsius plus 91 degrees Celsius, and then just divide them by 2. So this would be equal to, if we have 88 and we add 91, we get 179 degrees Celsius. Divide this by 2, and then 179 divided by 2 would give you 89.5 degrees. I mean, another way to do it that would be even easier than this would be, okay, if for every 1,000 meters you go up by 3 degrees Celsius, for every 500 meters you go up by 1.5 degrees Celsius, or you go down by 1.5 degrees Celsius. Therefore, 91 minus 1.5 would be 89.5 degrees Celsius. So that's my answer to part 1. It's going to be 89.5 degrees Celsius. B says, if the water boils at a temperature of 88 degrees Celsius, what altitude are you at? Okay, so 88 degrees, we actually have this on our diagram. So 88 degrees Celsius is located here, and at 88 degrees Celsius, my altitude is 4,000 meters. I can read that directly off of the chart. It would just be 4,000 meters. Okay, so that's our general rule. For every 1,000 meter increase in height, our boiling temperature of water drops by 3 degrees Celsius. Okay, that's it for today's lesson, and you can complete the assignment called Pressure and Thermometers, and I will talk to you in the next lesson.